I'll start by introducing myself. I'm Ben Thornton. I'm a consultant at MSC Software with a background in multibody dynamics. I'm here to talk about some interesting work that I've had the privilege of carrying out as part of a collaboration between Northrop Grumman and SmartUQ. So I hope you enjoy it. This presentation is a case study about migrating from a traditional trial and error design process toward a more modern process that uses surrogate modeling and numerical optimization. Here's an example of the trial and error process conducted last year at Northrop. The team started with an initial design which needed improvement. In this case, we wanted to reduce component stress and reduce input torque. We modified the design, evaluated it via simulation. When it still didn't meet the requirement, we repeated until eventually we arrived at an acceptable design. This probably sounds familiar. It's very common. It works, but it's unlikely to lead to a truly optimized design. You can see clearly that we improved on our initial design, but we thought we could reduce component stress further. However, our manual trials seem to be hitting a lower limit. So the team at Northrop decided to try a new approach called surrogate optimization. This approach allowed us to make radical improvement to the performance of our design. In this presentation, I'll describe what surrogate modeling is, how we implemented it, and what our outcomes were from using it. We'll start with a background on the Mk44 chain gun. This is the system we were designing it at Northrop. We'll talk about the traditional trial and error design approach. We'll talk about surrogate optimization, what it is, how we implemented it. We'll get into our specific outcomes and talk about future work. The Mk44 is a dual feed chain gun. It weighs in at 344 pounds, it fires at 200 shots per minute, and it has about 5,000 installs worldwide on a variety of sea, land, and air vehicles. The feed system is a fairly unique mechanism that relies on a highly irregularly shaped spring we call the round positioner spring, which controls the positioning of a roller plate which directs rounds from the feed to a rotor, which ultimately places them into the chamber. To make matters more complex, since this is a dual feed system, the single round positioner spring must redirect rounds from either feed path. The spring has two primary failure modes. The first being feed jam, characterized by excessive drive torque, usually caused by improper round positioning. And the second is spring fatigue, caused by cyclic contact between the spring and the round sprocket shaft. And so the design is driven by two primary metrics: drive torque, which needs to stay below a spec, and spring stress, which needs to be minimized. To evaluate our designs, we model the system using multibody dynamics simulation in MSC Adams. The model primarily uses rigid bodies, but of course the results are really driven by the spring behavior, which includes flexibility and contact. So the spring is modeled as a series of rigid bodies, but connected by Timoshenko beams. It has contact defined between the rigid bodies and the sprocket shafts and the rounds. We found that this approach is sufficiently accurate. It correlates well with test data and high-speed video, but it's also extremely efficient. This model runs in minutes. This modeling approach in Adams allows us to quickly conduct what-if studies. We can rapidly evaluate and compare design ideas to see what works and what doesn't. Before we talk about surrogate optimization, let's first review how numerical optimization would be performed directly on a physics-based simulation model. We'd start with an initial design. That would feed into an optimization loop that would successively generate design variants, check for convergence based on difference between successive variants, run simulations to evaluate the variant performance, and use the outputs to determine the next variant. Once the variants converge, the loop ends and returns the converged optimal design. This process can be quite cumbersome due to the high computational cost of the physics-based simulation, even with a model that runs in minutes. Surrogate modeling alleviates this high computational cost. A surrogate model is a statistical model that must be trained from the results of the physics-based model. But once a surrogate model is trained, it becomes trivial to run numerous evaluations. In surrogate optimization, the high-cost simulation is replaced by a low-cost surrogate model. Both the surrogate training and the optimization require the modeling to be fully automated and parameterized. So we had to reduce the spring geometry, which normally comes from a CAD package, to a set of algebraic equations with 8 parameters. Once it was parameterized, the modeling could be fully automated. We used Python libraries to solve the geometric spring shape equations, and we used the Adams scripting API to build the models. The first step in training the surrogate model is to predetermine a set of sample designs to train the model on. Remember that each design is a set of 8 parameters, so our training data is an n by 8 matrix. Sample selection, also known as design of experiments, must be done strategically. We used a constrained Latin hypercube scheme. This is a space filling method, which means that it seeks to evenly fill the design space. Because of the way the geometric spring shape equations were formulated, it was possible to select a set of parameters for which there is no solution, and this would generate unpredictable designs like this one. To prevent this, we used SmartUQ to generate a constrained Latin hypercube sample set. In SmartUQ, you can use Python functions to define constraints that each sample design must satisfy. This way, you avoid areas of the design space for which there is no geometric solution. Here's a set of 100 sample designs generated using the constrained Latin hypercube approach. When we generated the training designs, we didn't really know how many samples would be sufficient to train the surrogate model. So we used another feature in SmartUQ called slicing. This allows you to generate a Latin hypercube in several slices. Each slice is a Latin hypercube in itself, meaning that it evenly fills the design space. But any number of overlaid slices also results in a Latin hypercube that more densely fills the space. This approach allows you to train the surrogate model in phases until it reaches an adequate accuracy. We ultimately used 20 slices of 100 samples each, so 2,000 samples total, though this ended up being overkill in hindsight. Here we see how our surrogate model got more accurate with sample size. For each sample design, the surrogate model had to accurately predict stress and torque for both the lower and the upper feed configurations. We used the standardized CV error to evaluate the accuracy of the model. Ideally, we would have achieved values below 20% for all 4 predictions. We achieved this for both stress predictions, but we had to settle for less accurate torque predictions. This ended up not being an issue since our goal was just to keep the torque below spec. Stress, on the other hand, we wanted to minimize, so the accuracy of the stress predictions was crucial. We can also see that despite running 2,000 simulations, the accuracy was converged after 1,000. In hindsight, we could have stopped training the model there with the same outcome. In addition to the standardized CV error, another good way to evaluate the accuracy of the surrogate model is to conduct a validation study in which you set aside 20% of your available data for validation. The validation results can be visually evaluated using correlation plots as shown here for the stress predictions. Here you plot the actual physics-based simulation output on the x-axis and the corresponding surrogate prediction on the y-axis. Ideally, all the values would fall on the y equals x line shown. The accuracy can be quantified using the standardized root mean square error. Again, we were targeting 20% for this error. Here we see the same plots and error values for the input torque predictions. As expected, the model doesn't perform as well for the torque as it does for stress, but it was sufficient. Now that we had a sufficiently accurate surrogate model, we could perform our optimization. The method we use is called COBILA, or constrained optimization by linear approximations. It's a type of direct search optimization algorithm. It allows us to minimize one input, in our case, the peak stress over both feed configurations, while enforcing constraints on the inputs and other outputs. So we can enforce our geometric constraints discussed earlier, and we can also enforce that the torque remain well below the spec. With this approach, there's no guarantee that the optimizer will find a global optimum. The optimization requires that you give it an initial design. By running the optimization numerous times with different initial designs, we can be more confident that we've found a global optimum. We decided to use one of our DOE slices as a set of initial designs. That way we could run 100 optimizations with initial designs scattered evenly across the design space, and we'd be fairly confident that we'd found a near global optimum. The optimum design radically improved on our prior best design from the trial and error approach. With the upper feed active, the trial and error approach reduced the stress by 18% from the baseline design and the torque by 23%. The surrogate optimization design reduced these by 42% and 48%. With the lower feed active, the trial and error approach again reduced stress by 18% and made no reduction in torque. The surrogate optimization design reduced stress by 37% and torque by 29%. We can then model the optimized design back in Adams to study other aspects of the optimized spring performance and compare back to the baseline design. Here we see the upper feed results. The optimized response in blue has significantly reduced torque and stress compared to the baseline in black. You can also see that the spring still functions properly, delivering each round to the rotor. Here we see the lower feed results tell the same story. Significant reductions in torque and stress while maintaining proper functionality. This is really just the tip of the iceberg in this area. There's plenty of potential for additional studies using surrogate modeling on this program. One thing we'd like to do is include other design parameters. Here we focused on the spring shape, but we could easily apply the same methodology to optimize the design of the roller plate that attaches to the end of the spring. Another valuable study would be to quantify the uncertainty in our results. Uncertainty creeps up from a variety of sources like manufacturing tolerances, model input uncertainty, and model form uncertainty. Quantifying this uncertainty and using it in the optimization could lead to a more robust design that performs well even in fringe scenarios. We'd also like to include functional metrics in the optimization. Things like the margin between when the round enters the rotor and when the rotor turns, or the amount of force exerted on the round when being pushed into the rotor. And that wraps up my presentation. I hope you enjoyed watching. I'd like to send a quick thank you out to my co-authors, Jesse, Gavin, and Eric. If you're interested in any of the software I showed, they were Adams for the multibody dynamics and SmartUQ for the analytics. And of course, thank you to everyone who watched. Thanks for taking the time to do so. I hope you all enjoyed it, and I hope you enjoy the rest of the conference.